I'm going to go over some of the key points of each question. Feel free to email me with questions on any details that I'm skipping over. For the first one, Egyptian, note that these can be in any order. Hindu Arabic is our normal numeration system. Roman numerals, note that that 1 before the V means we're taking 1 away from 5 to give us 4. So this would be 24. Chinese, the biggest thing there is remembering that you do need to put a number in for the 100 value if we're dealing in hundreds. In this case, we just have 2 tens and then a 4. If, for example, it had been 324, we'd have the number for 3, the number for 100, and then 2 tens and a 4. Number 2, the Egyptian method of doubling. So first, we can choose either number to put over here and use the other one as our target. Doesn't really matter. It's probably easier to use the bigger number to be the one that we double, but it's going to give you the same answer. So we put 121, and essentially what we're trying to do is come up with what is 41 of these 121s. So over here, to do that, we're doubling each time, and we're doubling over here. So this tells us, for example, 4 121s would give us 484. 8 121s would give us 968. You might need to work out some scratch work here. Once you've gone up to at least halfway of your target number, in our case 41, you can quit, and then it's a matter of figuring out how to make that target number using these numbers on the left. If you would put this into base 2, if you really can't figure it out, if you put this number into an exploding dots machine, and then basically if there's a dot in a block, that would tell you need to circle the number. This would be the block on the right, the second one from the right, third on the right, and so on. If you can't figure out how to create this target number just using these multiples of 2. Once you figure out how to make that target number with multiples of 2, you circle any of these terms and then add them together. Notice here I'm just adding left to right since we discussed that in class, how you could do it. You can, of course, add right to left if you feel more comfortable with that. So our answer is 4,961. I'd encourage you to check using normal multiplication methods that you're used to. Remember, the purpose of this was they only knew how to add and subtract. They couldn't multiply, and that's why they needed a method like this. Number 3, so we have 214 in a 5-to-1 machine, so we could go ahead and draw that into our 5-to-1 machine. Then we want to label what each of those dots represents. For example, this dot is much more powerful than this dot is, and we can do that by doing powers of whatever our base is. So this will always be our 1s. This would be our 5 to the first power, 5 to the second power, 5 to the third power, and so on. In our case, we don't have anything past 5 to the second power, so we add them up. This is just going backwards in the opposite process. Essentially, we'd be putting 214 dots into this compartment and then doing the explosions until we couldn't explode anymore. More practically, it's better to, again, use that system of figuring out what each compartment would represent. So a dot in this compartment would be 125, which is 5 to the third power. Here would be 5 to the fourth power, or 625. Once you go out so that you're above the number you're trying to figure out, you can figure out how many of these 125s would go in to the 214 without going over it. So in that case, we can only get 1. If we put in 2 dots, we'd already be at 250, and that would be more than what we're trying to represent. So we put in 1, subtract it out from the 214 to find that we still need 89 to account for. You could do 125 at a time and then subtract 25 from 89. If your number is still bigger than 25, do another one. Or you might notice that you can knock 3 of them out at once and then just subtract 75 off of the 89 we still have left to represent. Then we have 14 left to go. We can get 2 5s out of that. That would leave us with 4. So putting that in base 5 notation, we'd have 1, 3, 2, 4, and don't forget that little 5 that tells us this number is written in base 5. Okay, division. Regardless of the base that we're in, first we would want to, or sorry, this is addition, I'm sorry. Base 3, we could make 2 separate machines for each of these and then combine them in a third one. I think it's just as easy to put the top number across the top, or the first number across the top, the second number across the bottom, and then start combining. So originally I would have had 1, 2, 1, 2, and I would have had these two. I would not have had that, and I would have had these two. Once I start making the explosions, anywhere where I see 3 dots, I explode to the left until I can't go any further, and at that point I'd have 2, 1, 2, 1. Subtraction, same idea. You'd put the 1, 2, 1, 2 across the top, and then since the bottom is negative, we're adding a negative number here, so we're adding 2, 2, 1. I would draw that 2, and that 1 as antidots, as these open dots. Once I do that, I have a slight problem where I have too many antidots and I need more positive dots to cancel them out, and so that's why I have to explode, or implode actually, this dot backwards. If it takes 3 dots to give us 1 in this direction, if we take one dot backwards, it becomes 3 dots, and then that would allow us to cancel out these 2 antidots. Same thing here, implode 1 into 3, and that would allow us to cancel out the 2 antidots here. Here we already have 1 to cancel out the antidot, and so we'd end up with 2, 2, 1, base 3. Division, 1, 2, 1, 2. So we're doing 1, 2, 1, 2. The pattern we're looking for is 1, 0, 1. So we're looking at starting from the left, I would say is easier in case there's a remainder, although I won't give you a question with a remainder on the test. So here we'd have 1 space 1, and we'd put the tally over the rightmost box, and then 1, 0, 1, tally, 1, 0, 1, tally, which would give us 1, 2 in base 3. For the GCD and LCM, I would start by doing the prime factorization, so breaking it apart into factors. Notice that you could have taken the 24 into 2 and 12, or 6 and 4. It doesn't matter as long as you keep going down until the primes. That's the beautiful thing about primes, is that there's only one end result you can get in terms of the primes. Once you get that, rewrite the 2 numbers in terms of their primes. So notice we had 2 times 2 times 2 there, which is why we have 2 to the third. The GCD is a greatest common divisor. So since we have to divide into both numbers, we want the smallest possible power of each prime. So for the 2, the smallest power would be 2 to the first, which is why we write 2 here. For 3, the smallest is 3 to the first. It's the same for both of them. For 7, the smallest power is 7 to the 0th, or not even having a 7, which is why we don't have a 7 here. If we did put a 7 here, notice that our number would no longer be able to divide into this number on top, because there is no 7 in the prime factorization of it. Once we get that, we multiply them to get our GCD. Our LCM is the opposite process. We want to make sure that we're a multiple of both numbers, so we need the highest power of each prime. So in this case it would be 2 to the third. We'd still have 3 to the first, and we'd want 7 to the first would be the highest power of 7. Multiply that out, you get 168. You can check your answer by multiplying the original two, 24 and 42. That would give you 1008. And multiplying your GCD and LCM, which would also give you 1008. Those two should be the same number. If they're not, go back something along the way it was a miscalculation. If we're looking for whether a single number is prime, we want to take the square root of that number, and then we want to go up until that square root. So notice that whatever this 113 is, the square root of 113, it's less than 11, because 11 squared would give us 121. So 113, the square root of that must be something less than 11. So we just need to check the primes that are less than 11, which are 2, 3, 5, and 7. We can use our divisibility tests. We can also use long division. Either way is fine. 2 does not go into 3. The final digit there isn't even, which means the entire number isn't even. So 2 is not going to go into 113. We can add the digits and see if 3 goes into that sum, which it doesn't. So 3 doesn't go into 113. Doesn't end in a 5 or 0, so 5 doesn't go into it. And if we do a long division on 7, there's not a quick divisibility test for 7, so long division is probably our best bet. Notice there would be a remainder there. It doesn't even matter what it is. Because there's a remainder, 7 does not go into 113. Since none of those primes go into 113, we know that no other numbers will go into 113, and so 113 is prime. A much quicker method, especially when we have a large batch of numbers, is the Sieve of Eratosthenes. And to do that, we need to do all the primes up to the square root of 139. Whatever the square root of that is, it's less than 12, because 12 squared would be 144. So we need to check 2, 3, 5, 7. This time we do need to check 11 also, because 11 squared would be less than 139. It's possible there are multiples of 11 here. And we need to find the first number in the list that each of these numbers goes into, and then we can just skip by that same value. So for example, 2, the first number that 2 goes into is 120, then we skip by 2's, 122, 124, 126. Each time we're crossing these numbers out through 138. Then we get the first number that 3 goes into. It turns out to be 120. Notice that 1 plus 2 plus 0 is 3. 3 divides into 3, so 3 divides into 120. So I'm crossing that out and then skipping 3, 1, 2, cross this out, 1, 2, cross this out, 1, 2, cross 129 out, and so on. 5, 120 would be the first number it goes into. 7, 126 would be the first number. There you might actually have to count up from 70 until you figure out the first number that 7 goes into. The same for 11, unless you know that 11 squared is 121, and then you would count 11 and cross off. After you've crossed off all of the multiples of these primes, anything remaining must be prime. So here we have 4 primes left. 1 is not a prime, mostly because of that property we mentioned earlier. We want every positive number 2 or greater to be expressible as a prime number or as a product of primes in a unique way. The unique word is important there. If 1 was a prime, you could have any positive number, for example 10, and express it in many different ways, and that would just create a lot of messiness in a lot of the proofs that we do. 12 and 13, I'm going to let you work out. If you have questions, let me know. 2 negatives, if you have minus a negative, that would be a positive number. Also down here, we're looking for a common denominator. It doesn't have to be 12. You could use 24. That would work just as well. Notice that 2 I'm changing to 2 over 1 just for convenience in multiplying. I'm also reducing a little bit so that I'm in lowest terms once I get my answer. Equivalence in a certain mod, you can think of it in 2 ways. If you would put it into the dot machine of whatever that mod number is, and there's the same number of dots in that last compartment, that right compartment, then the 2 numbers would be equivalent. For example, if we added 2 more dots here, then we'd have 4 dots in that right compartment, and that number would be equivalent to 4 in mod 5. So if we added 2 dots there, that would give us the number 9. 9 would be equivalent to 4, but it would have to have the same number of dots in that rightmost column. Another way to look at it is simply to subtract the 2 numbers you're comparing. So if we're looking at 7 and 4, 7 minus 4 would give you 3. If your mod or your mod doesn't go into that number evenly, then the 2 numbers aren't equivalent. Why did I pick 7? I wouldn't have had to. I could have chosen any number as long as it didn't have 4 dots in the rightmost column.